Alright, we're back once again and we're doing Bayesian naive Bayes. And we're going to get a cool Bayesian, fully Bayesian classifier. So we are looking at this predictive distribution here. And we wrote that it was proportional to this thing. And we started integrating out our parameters. And we found that in order, well, it's okay, so I should put a d theta here to be precise. We found that in order to evaluate this thing, we needed to, well, we just wrote out some expressions for what they were, and we ended up down here with this wonderful, very attractive, very good looking Dirichlet categorical conjugacy products. And now let's go ahead and apply from using the Dirichlet categorical conjugacy. We can simplify these. This one becomes, I'll use the same blue here, maybe a little different blue. This one, the Dirichlet absorbs the categorical. So this becomes a Dirichlet on pi with parameter alpha plus, let's say, c. There's going to be more, but let me tell you what c is. C, let's see, what do we want to say? C k, I guess, is the number of y, it's the number of i's such that yi equals k. This was from the video on the Dirichlet categorical conjugacy. And this part, product over j and k, again, the Dirichlet absorbs the categorical, and we get a Dirichlet over rjk with parameter beta plus, let's see, d, and it's going to depend on j and k, so let's put djk, I guess, something like that. And here, so it's a little bit trickier because we've got this indicator here. So let's think about that for a sec. So we've got a Dirichlet, and we've got, for each, so fixed sum j and k. Think about, for particular j and k, we've got a Dirichlet, and we've got a product of categoricals. And the only ones which appear are the ones where yi equals k. So when we were looking at this conjugacy, we were counting the number, so like for this one here, we were counting the number of yi's, so it's the number of products, the number of factors in this product for which yi equals k. And here, in order to count the number of factors in the product for which yij equals a particular value, we will only consider the ones where yi equals k. So this djk, well, let's see, the elf element of that, this is a vector, and the elf element of that vector is going to be the number of points I, the number of things in this product, for which ij, or xij equals L, that's the element of the vector, and yi equals k. Because remember, we're only counting the ones where yi equals k. That's where the factor shows up. So these are our counts, and we get using the Dirichlet categorical conjugacy, we get this product of factors here for this thing A. All right, so that's looking good. And now let's go back up to our original thing here. Let's look at this. Let's plug in what we found for A into this integral and see what happens. So let's rewrite this again down here. So we've got this thing is proportional to the integral of this times A. Let's rewrite that. The predictive distribution on y given x and the data equals, or is proportional to, the integral of, well, I'll write it here, probability of x and y given theta times A, that thing A, and that was this right here. or this rather, times Dirichlet pi with parameter Dirichlet over pi with parameters alpha plus c times this product over j and k of the Dirichlets over rjk with parameters beta plus djk. And we're integrating all of this stuff with respect to d theta, all those parameters. Now this part, we came up with our nice little expression for this part, which was this thing. So that's the probability of y times product over j and k of rjk xj to that indicator. So let's put that. Probability of y times product over j and k rjk of xj to the indicator that y equals k, right? Let's see those. Yep, that's right. And now, okay, now we're gonna integrate. So remember, this was an integral over all. So this is like integrating over pi, each of the coordinates of pi, integrating over r11, integrating over r12, all the different r's. So over whatever it is, r, I don't know, m, n, I think. So we're integrating over all of these things. And by the linearity of integration, we can, this is a whole bunch of integrals here. And we can move them through, we can pull stuff out that doesn't depend on what we're integrating with respect to. So let's do that. So this becomes, we can pull together all the things that only depend on pi here. So let's do that. So let's pull together the pi stuff. So we get pi of y times the Dirichlet on pi with parameters alpha plus c. Okay, that's all the pi stuff. Now let's pull together, let's see. Let's think about a particular j and k, and let's pull together all the j and k, all the stuff for rjk. So all these guys factor, so we can go ahead and write this as a product over of the integrals rjk xj to the indicator y equals k times the Dirichlet for that rjk. So it's Dirichlet of rjk with parameter beta plus djk. And oh, I should have written here, there's what we're integrating with respect to in this part. Let me squeeze it in there. With this one, we're going to pull in the integral over pi, because right, this is all of this stuff was a constant. All of this was a constant with respect to all these other rjk's and stuff. And this one we're integrating with respect to rjk. We're integrating with respect to all the different coordinates of this vector rjk. All right, now things are looking very good. So let's see what we can do here. This is looking good. Let's look at this one first. What is this? Well, this is just the expected value, right? We're integrating with respect to a probability distribution. So this is just the expected value of pi of y under this posterior distribution. And so this is just, we know how to compute the expected value. We know what the expected value of a Dirichlet distribution is. And so the expected value of this, the expectation of this Dirichlet distribution for the yth vector, the yth component, is just alpha y plus cy divided by the sum of all these. So maybe I'll just write the sum of all those over y. So that's all that part is. And now let's think about each of these factors. So here we have something very similar, right? These are expectations also with respect to the distributions on rjk. But so let's think about if k equals, well, first if k doesn't equal y, So in one of these, in those factors for which k doesn't equal y, this is 0, so this is just 1. And then we're integrating with respect to a probability density, so that just integrates to 1. So for all the ones where y does not equal k, they just drop out. They just become 1. And we're left with the ones where k equals y, so all we have to do is take the product over j from 1 to d, and it's the expectation for those when k equals y rather, it's just the expectation of rjk of xj. It's the xjth coordinate of this Dirichlet distributed random variable. And that, just like before, that is beta xj, it's the xjth coordinate, plus djk of xj, the xjth coordinate of this vector, divided by the sum of this over all, let me say over all, what do I want to say? I guess k is fine. bk plus d, oh, I can't use k again. My goodness. I already used k. Let's say over all L, from 1 to n, bl djk of L. And these are, let's just rewrite the denominators, pretty it up a little bit. This is alpha y plus cy. I'm going to run out of space there. Let me go to the next line. This equals alpha y plus cy divided by the sum of the alphas. Let's define that to be alpha 0. We'll just pretty this up a little bit. Plus the sum of the cy's. And what's the sum of the cy's? Cy, or ck, if we summed over k, sum over k of ck, that is, so ck was the number of points for which yi equals k. But every, yi is equal to k for some k. I mean, for any I, yi equals some k. So if we sum this up over k, we just get the total number of points, which is n. So this is just n. And now we have this product, j from 1 to d. And we have beta xj plus djk of xj. So our parameters plus our counts. Divided by, let's call b0 the sum of the BLs. So alpha 0 equals sum of the alphas. And beta 0 equals the sum of the betas. So overall y's from 1 to n. That's overall L from 1 to capital N. And what's the sum of these djk's over L? Well, djk was this thing. It was the number of points for which the jth coordinate equals L and y equals k. And if we sum over all the, what are we summing over? We're summing over L. Right. Okay. So if we sum over L, every, for any point, the jth coordinate, it has to be equal to L for some L. So this part, as we're going through and we're checking each point, we're counting, okay, is this satisfied and is this satisfied? Well, this is always satisfied for some L, so since we're summing over the L's, we don't need to even count, consider this part. So we just are counting the number of points for which yi equals k. If you write these out in indicator functions, it's a little more clear, but as a sum of indicator functions. But anyway, so that ends up just being the sum of the ones for which yi equals k, and that's just, what's that? That's just ck. Wait, where did k go? Oh, this should be y, sorry. Okay, I'm out of time in this video. Let me come back one more and we'll wrap this up.